Good morning. So, I'm very sorry that we couldn't talk yesterday and that I wasn't able to go through the presentation, but I hope this video will be a good substitute. So, I'd like to do three things during this video, and I hope it won't be too long and will be interesting for you. The first is to go through a presentation that introduces LEAP-IBC, how it works, what the philosophy behind it is. The second thing I'd like to do is to give a practical demonstration to show you LEAP working and to give you a sort of flavor of how the software works. And the third thing is, just at the end, I'd like to go through some next steps or potential next steps to use LEAP-IBC for developing a dataset for Chwani. And that'll include sort of trainings that we can do online and in person, and then the steps that we need to do to develop a dataset for Chwani itself. But before I get to that, let me go through this presentation. So, LEAP stands for the Long Range Energy Alternatives Planning Tool. And the first and probably most important thing to emphasize is LEAP is not a model. There's no such thing as the LEAP model. It's a tool that you can use to create models, and that might be models of emissions, it might be models of an energy sector. But the point about that is that SEI and LEAP does not have any information baked into it that cannot be changed by the user. So you're really in control of how you develop this data set, and LEAP is flexible in terms of how you estimate emissions from different sectors. So if we go through the name of LEAP, long range, the reason it's the long range energy alternatives planning system is that it's really designed for looking at scenarios, looking at making projections into the future to assess how emissions or how your energy or non-energy sectors are likely to change in response to trends in socioeconomic development, but also from the implementation of different policies. So that's the long range. Generally, people use LEAP for looking at projections, maybe out to 2030 or to 2050. And then it was the energy alternatives planning tool. So LEAP started life in the 1990s as an energy planning tool. It was designed to look at the energy system, and then gradually it has built up over time to look at greenhouse gas emissions from the energy system. And over the last 5 years, we have increased the ability of LEAP to be able to look at air pollutant emissions, both from the energy sector, where the majority of air pollutant emissions come from in most countries, but also to include non-energy sources like waste, agriculture, industrial processes like cement production. So within LEAP, you can capture all the major energy and non-energy sources of your emissions. So like I said, LEAP is a flexible tool that supports different methodologies for estimating emissions. So this will be important when we come to discussing what we can do in Chwani. But LEAP can support both very top-down methodologies where we take aggregated data like energy consumption in particular sectors, and we use that combined with an emission factor to estimate emissions. It also supports bottom-up methodologies. For example, in the residential sector, we could say how many households we have in Chwani, then how many of those households cook using different types of fuels and technologies, like LPG, like electricity, like charcoal or other solid biomass. And then we can say, well, how much energy does a household using those different types of fuels use for cooking? And then LEAP will calculate the total energy consumption, which we combine with an emission factor to estimate our emissions. So that becomes a much more bottom-up methodology. Like I said, LEAP is scenario based, so we can look at different policies, different assumptions depending on our interest, and see how does that affect our emissions. And it can be used at various scales. It can be used at the national scale and the municipal scale. It can be used with different regions within a country as well to look at how they all add up to national emissions. This is a brief history of LEAP. Maybe the thing to highlight is in 2015 is when we developed and launched LEAP-IBC. The IBC allows us to take the emission estimates, which was the traditional endpoint of a LEAP analysis, and convert them into air pollution concentrations and impacts on human health. So I'm going to spend some time on this slide, and I'd like to have my pointer to be able to show you different aspects of it, because this is really the skeleton, the framework within which LEAP works. So it's important to understand this diagram to understand how LEAP calculates emissions and does its modelling. So at the top here in LEAP, we have some what are called key assumptions. These are external variables that are used to create our projections, to drive the model in LEAP. So this might be information on demographics, like population. It might be macroeconomic indicators like GDP or the value added from industry or services or agriculture to the economy. And these may be projected over time, and this is something that is added externally to LEAP. And what that does is then drive our energy and non-energy sector models, which are really at the heart of LEAP here. So within our energy sector, which is here, LEAP is what is called a demand-driven model. So the demand for energy, the demand for different types of fuels drives everything else in our energy sector model. So we start off with a demand analysis. And the sectors that we might cover within a demand analysis include the residential sector, the transport sector, industry, commercial and public services, and agricultural energy consumption. And for each of those sectors, we need to tell LEAP how much energy is consumed within those sectors. We can do that in different ways. We can use a top-down approach where we just say in the residential sector, this is how much energy is consumed. Or we can do something that is much more bottom-up, where we have more detail on how energy is consumed within different subsectors in the residential sector or in the transport sector. But the output from this demand analysis is to say, across Chwane or across South Africa, how much energy is consumed in terms of how much electricity is consumed, how much diesel, how much gasoline, how much coal. All of that comes out of this demand analysis. And then that drives our second module here, transformation. Transformation is where we convert energy from one form into another. So the most obvious example here of energy transformation is the generation of electricity. So in this module here, we will represent electricity generation. So we might have coal going to electricity, we might have renewables going to electricity like wind and solar, nuclear to electricity, natural gas to electricity. And we can represent that at different levels as well. We could include individual power plants, or we could include just aggregated data like total renewables going to electricity rather than individual solar farms, or natural gas going to electricity rather than individual natural gas power plants. Other sectors that we would include here would be oil and gas production, charcoal making, coke manufacture, other processes where we're converting a primary fuel into a secondary fuel. Our energy sector model is completed by these two resource modules here that look at the depletion of different resources. But there are no emissions associated with this, so I don't think we would need to focus on these. Then we have our non-energy sector analysis. And the non-energy sector analysis is external to our energy module and can support a variety of different modeling methodologies. I'm going to come on to later to talking about a default LEAP-IBC dataset where we have already entered default modeling methodologies using the Intergovernmental Panel on Climate Change, the IPCC emission inventory guidance, and input their tier 1 or tier 2 methods for all of the different sectors. So we can include that here. And these external variables, the demographics, the macroeconomics, or other variables, are used to create projections across all of these different modules. So to project how our energy demand is going to change and what that means for our transformation, for our electricity generation, or what that means in terms of projections in the number of livestock or the crop production that we will have in the agricultural sector. At every point down this branch, we can specify and what is called in LEAP an environmental loading, but it's really just an emission factor. You can specify an emission factor to calculate the emissions of different pollutants. Those emissions of different pollutants are then passed to the IBC calculator to calculate the change in air pollution concentrations, the change in PM2.5 concentrations, and the impact that has on human health. They're also used to calculate the global average temperature change resulting from those emissions. So we can look at the impact on climate as well. So I hope that makes sense. When developing the LEAP dataset, we would need to discuss exactly how you would like to look at different sectors. But typically, the input data that is required are data on demographics, on population, on GDP, data from an energy balance, if you have that for the city, or from surveys and audits. So if you have something like a household survey or a census, that can provide very useful information that we can use for different sectors. If you have developed emission inventories previously, the activity data and the emission factor from those inventories can be very useful. And then, of course, for generating scenarios, understanding the different plans and policies that you have in place for climate, for energy, for air pollution, can allow us to represent those in the model. And generally, the outputs that you can get from LEAP are varied. They include energy supply, energy demand, so you can look at your energy system, which may not be so interesting for you. The main outputs that I think you might be interested in would be the emissions of air pollutants, the emissions of greenhouse gases, and their impact on human health and on climate. So I'm not going to go into much detail about the user interface just now because I'm going to show you LEAP once I finish this presentation. But the thing that I do want to emphasize is the way in which data is stored in LEAP. And the way that data is stored is through a tree structure. So this tree has different branches that represent different source sectors. you have different types of branches to represent different fuels and technologies or different pollutants. And this tree structure is flexible. It is not fixed. So you can change the types of branches you have under your demand sector. You can change the branches you have under transformation. But this is the way that data is organized and stored in LEAP. So LEAP-IBC was envisaged as a tool for looking at air pollution and climate change strategies. And it was designed to allow users of LEAP to be able to look at the air pollution and climate change impacts of their different emission scenarios. So what does this mean for the actual impacts that we care about? So a traditional LEAP analysis would stop at this point here at emissions. What the IBC module does is take the emissions from LEAP and model their chemical reaction and transport in the atmosphere to estimate the exposure of people to fine particulate matter, to PM2.5. So we go from emissions to estimating concentrations and exposure of PM2.5. And then we estimate the impact that that has on human health. We also calculate the change in radiative forcing, the change in the Earth's energy balance from the emissions that we calculate in LEAP, and convert that into the impact of those emissions on global average temperature change. So we're really trying to get at the impacts, the consequences of emissions, and how they change for different emission scenarios. So to do that, to use IBC, there are some restrictions compared to a traditional LEAP analysis, which is very flexible. The first is that we need to cover the total emissions of a range of different pollutants. So we need to look at all of the pollutants that contribute to PM2.5 concentrations, and we need to capture our major greenhouse gases as well. Within LEAP or within the IBC calculation, we also need to capture the emissions coming from outside our city or outside our country. Because the impact of air quality in Chwane is not just determined by Chwane, it's also determined by other emissions in other areas of South Africa and of other countries as well. So we have some default emission scenarios to represent the rest of the world emissions, and this is taken from an international database from the IASA GAINS model, and they are used to represent emissions outside of our city. The IBC module then takes these emissions that we calculate for our city and then the rest of the world into the concentrations of PM2.5 and calculates the impact on human health and global average temperature change. And this is all then displayed in LEAP so that you don't need to go to a separate program. This is calculated automatically and fed back into LEAP. The IBC calculates PM2.5 concentrations using a atmospheric chemistry transport model. And this model is called Geoschem Adjoint. Geoschem Adjoint tells you for an emission in a particular grid square across the world what the impact that emission has on air pollution concentrations in your city, in Chwane. So it says for an emission in Chwane, what impact does that have on PM2.5? But it also says for an emission in another part of South Africa that is covered by a different grid square, or an emission in the UK or in any other country, what the impact it has on air pollution concentrations in Chwane. And obviously for a grid square in the UK, the impact on air quality in Chwane is going to be very, very, very small. We then combine those with international concentration response functions that say for a particular emission of for a particular exposure that a population has to PM2.5, what impact does that have on human health in terms of premature mortality, the number of premature deaths that occur due to that exposure to PM2.5. So urban LEAP-IBC is now being developed. So we developed the IBC module at national scale, but we are now developing it for urban scale and will be providing the coefficients, this modeling for Chwane. The important thing is that in developing the data set, the emission model for Chwane needs to be nested within a national model for South Africa. So we would need to develop a emission inventory for South Africa and then one for Chwane as well. But I think that should not be so much of an issue. I think most of the data that we would need to develop an emission inventory for South Africa would be readily available. And it would be very good to discuss with you what information is available for Chwane. So the limitations of LEAP-IBC, like I say, the all pollutant emissions need to be covered from all sources to be able to calculate the emissions. Currently, the LEAP-IBC needs to begin in 2010. That needs to be the first year of the modelling. And the way in which the Geoschem adjoint model represents the transport and chemical reaction of pollutants in the atmosphere is linear. So it says for a change in emissions, there is a linear response in terms of the change in concentration. So non-linear atmospheric processes, non-linear atmospheric chemistry is not represented within this modeling framework. And then for the health impacts, we are using concentration response functions that are mainly based on research from North America and from Europe, and we are assuming that they apply globally. So I'm going to talk more about accessing LEAP and LEAP-IBC after I've presented it to you. So I'm going to go through that later. So when we're developing a LEAP analysis, there are three main steps, three main processes that we go through. The first is to develop a historical emission inventory. So we'd maybe pick 2010, or we could pick a range of years from 2010 to 2017 or 2018, depending on what data is available. And we would develop a historical emission inventory to capture emissions for all major sources from that historical year. We then develop a baseline scenario projecting emissions from our last historical year, maybe 2018, into the future to 2030 or 2040 or 2050, depending on what you think is most useful, to develop a baseline scenario of how we expect things to change. So this is our reference scenario, which we can use to compare with other scenarios. And these would be our then mitigation scenarios. So we would think about the mitigation measures, the policies, the plans that you would like to represent, whether that's increasing vehicle emission standards in the transport sector, whether that is action in the waste sector, energy efficiency, increasing renewable energy for electricity generation. Could look at all of those, represent them as different mitigation scenarios, and then compare them to our baseline scenario to see what the reduction in emissions, what the reduction in impacts are from implementing those mitigation measures. So I wanted to provide a quick example of the work that we've done in Ghana in terms of some of the outputs that can be provided from this analysis. So like I said, in Ghana, they have gone through this process of developing a baseline scenario, of developing a historical emission inventory, a baseline scenario, and the mitigation measures. So they have an emission inventory of different pollutants for 2017. They can see where the major sources of black carbon, for example, come from, residential cooking. And then for methane, the major source is landfill gas from the waste sector. And for carbon dioxide, they have electricity supply, and for NOx, electricity supply and industry were the largest sources in across the whole of Ghana. So this is a national scale analysis. But what it shows is that you can look at greenhouse gases, you can look at air pollutants in the same analysis and get a consistent estimate of the contribution of different sources to those different pollutants. What they then did was create different scenarios that represented the implementation of 15 different policies and measures. So they have a policy of increasing the LPG that is used for cooking, increasing the amount of solar systems in place, transport measures to increase CNG buses, to stop open burning of waste, improve cook stoves, more renewable electricity, vehicle emission standards, etc. And what that allowed them to produce was these results showing the progression of emissions for different groups of policies. So the red line here is their baseline scenario. Then you have different policies here. The yellow line is the full implementation of their climate change commitment. And the green line shows what would happen if they took additional action on a group of pollutants called short-lived climate pollutants. So these are air pollutants and they also affect climate. So this would substantially reduce black carbon emissions. For methane, you have your baseline scenario, and this is the effect of implementing your climate change plans, and then the full implementation of all of those 15 measures. And we can see the same for carbon dioxide. With the IBC, what this allows us to do is to translate that into impacts. So this shows the global average temperature change from implementing those different policies, but maybe more relevant for you is this graph that shows the number of premature deaths associated with exposure to air pollution. Now, Ghana is a small country in West Africa, so you have a large contribution, if we look at 2010, a large contribution from emissions in the rest of the world to air pollution in Ghana. We have a large contribution from natural background because during particular parts of the year there is desert dust that is blown down from the Sahara. And then we have this contribution here from national emissions. And between 2010 and 2040, the number of premature deaths is set to double. Now that's due to increasing air pollution concentrations, increasing emissions, increasing concentrations, but it is also due to increases in population and having an older population that are more susceptible to air pollution. The implementation of those 15 policies would avoid this number of premature deaths. Now that may look small compared to this large fraction here, but the real comparison, what we should compare this red bar to, is the yellow bar, which is the contribution of national emissions. And actually, and this is what Ghana can control. And actually, if we look at this reduction, we are reducing the number of premature deaths caused by Ghana's emissions by 1/3. So we've got a 33% reduction in the contribution of Ghana's emissions to air pollution health impacts, which is pretty good. So just to finish, Ghana is then using this analysis to support the development of a national action plan to reduce short-lived climate pollutants. And the IBC allows them to summarize the effect of implementing this plan in three key statistics. Full implementation of this plan would avoid 2,500 premature deaths per year in 2040. It would also avoid crop loss because ozone, another air pollutant, is damaging crops. It would reduce that. And it would reduce Ghana's contribution to global temperature change by 55%. And they are now identifying the actions needed to implement these priority measures. So the final thing that I'll say on this presentation is to talk about this data set which we call ASEANA. So ASEANA is our fictional example country that we use in one of the exercises that we can do. It's a default LEAP-IBC template that is set up to be compatible with the IBC module and to allow for integrated air pollution and climate change analysis. The reason that it allows for this type of analysis is it contains default methodologies to estimate emissions from all major source sectors and contains some default data that might be useful for that might save time and be useful for this type of analysis. First, it includes default emission factors for 11 pollutants, including greenhouse gases, short-lived climate pollutants and air pollutants. And we take these from the European Environment Agency, Emission Inventory Guidance, the Intergovernmental Panel on Climate Change Guidance, as well as scientific literature. So this ASEANA model, these are all the source sectors that are covered. The model can be easily changed. And the way in which countries have used it, or cities can use it, is to add specific data that you have available to make this data set specific for your city. We can also change the modeling methodology. We can go to tier 2 or tier 3 methods that are more complicated and give a more accurate estimate of emissions if the data is available. We can also add additional sources if there are sources that are not covered or that need to be taken to be made explicit, to be not added together with other sources. Then we can do that as well if they're very important. So this is really just intended to be a starting point that can be easily modified by users to make it specific for your city or for your country. So that's the presentation. What I would like to do now is to give you an overview of how LEAP works. And let me use the magnifier here to be able to zoom into the parts of LEAP that I would like to show you. So this is what LEAP looks like. The first thing that we do, so I've opened up a data set, ASEANA 411, which is our starter data set. And I can provide this to you for Chwane, that you can then add to as well. We could use this as our starting point to be able to save time. When we open the LEAP dataset, a good place to start is in this basic parameters screen, because it tells us exactly how our data set is set up. So in our basic parameters screen, we have here the different types of analysis that we can switch on and off in our LEAP dataset. So do we want to look at transformation and resources? Well, yes, we do, because that covers electricity generation, and there are emissions associated with that, so we want to do that. Energy sector effect loadings and non-energy sector effect loadings. That means, do we want to look at the emissions from the energy and the non-energy sector? Yes, so we have those checked. Complex effects means, do we want to look at things beyond basic greenhouse gases? Yes. And we've checked IBC as well, because we want to look at that. For the default ASIANA dataset, this is a national scale dataset, so we want to it to be a national scale dataset, and the ASIANA dataset is actually based on Bangladesh, so that's the country that I'm going to select there. Then the years, our base year is the first year of our analysis, and that is set to 2010. Then our first scenario year is the first year that we want to make a projection for. And in this case, we want to set that to 2011. So in this case, we're only going to have one historical year, 2010, and then our 2011 will be a projection. But we can change that and put whatever year we want as the first scenario year. We can create multiple historical years if we want to. Our end year is 2050, and we want to get results every 10 years. So this gives us an overview of our basic LEAP dataset. Down the left-hand side of LEAP, we have what are called different views. And there are two views that are really important: analysis and results. Analysis is where we build our data set, where we enter our data. It's where you spend 95% of your time in LEAP. And results, as you might imagine, is where we then view the results. So next to the views, we then have our tree structure. This is where we have the model of our emissions and where we enter data into LEAP. And you might recognize the names here from the skeleton, the diagram that I showed in the presentation. Our key assumptions here have demographics, they have economics. They also have other variables associated with the IBC. So to be able to estimate the impact on health, we need to know the disease rates for different types of diseases. And we have default data available for that. But if I focus on demographics and focus on economics, I think they show very clearly how we enter data into LEAP. And we do it in two ways. So the first is, if I look at population, the population that I have in ASIANA in my country is 41 million people. Now this has been entered directly as a number. So we can simply, if we want to change that, just delete what is there and enter a new number. So this is in our scenario current accounts. If I change my scenario from current accounts to baseline, you can see that my graph at the bottom here changes. We've now not just got a value for 1 year, we now have a graph that shows how the population is changing from 2010 to 2050. And there's a gradual increase from 40 to 55 million people. How have we entered that? How have we created this line? So if I go to Builder, I can see my expression that I've entered. And this is a little expression, a piece of code that explains how we are projecting our population. And it uses a function called interp. You can see in the help box here, it explains what interp does. It takes different values. So 2015 is our year, and then we've got our value, 43 million. 2020 is our year, 45 million. 2025, 47 million. What the interp function does is draw a straight line between these values to create an estimate of population for every year. So if you look at 2015, 43 million, 2020, 45 million. If I look at 2015, here I have 43 million. 2020, 45 million. In 2016 and 2017, I just have an interpolation of those values. So I get a value for every year. So this interp function is really useful. It means that if I have data for some years but not others, I can simply interpolate between those years to get an estimate of the values. So a common question that is asked, well, how do I need to type out that expression? Do I need to type in all that data manually because it's going to take me a very long time? And the answer is no. There are different ways that we can enter this data into LEAP. One of the easiest and most common is to set up our data in Excel to facilitate it being easy to enter into LEAP. So if I make up some population data, let's say to 2050. So my population was 41 million, then it goes to 47 million. I'm just making up these values, 42, 57, 62, 60, 54, 73. These are completely unrealistic, but I just want to make it so that you can see how it works. If I set this up with the year and then the values underneath, I can copy it from Excel and then I can paste it into LEAP. So now I have this variable. Everything has been formatted correctly. I've got the interp function 2010 41, 2015 47, for example. So this is now entered in the expression correctly for my population data. And if we see the chart, we then see that increase in population. And I can go in and edit that if I want to, because this data looks like it's not correct, because we've got these decreases and then increases in population. So let me create something that looks a bit more like what we had previously. So I can edit the data there, and then I get something that is increasing to approximately the same rate as we had previously. So that's an overview of how we enter data in LEAP. If I go look at economics, I have the GDP of my country, billion US dollars. But then this variable here is average income, GDP per capita. And if I look, this isn't a number that has been entered. It is an equation. It is referring to two other variables. So it's referring to GDP, which is stored here. It then refers to key demographics population, which refers to this branch path, key demographics population. So the average income is not something that we enter. It is calculated from two other variables. The other thing I want to show you under economics is another function that is very commonly used in LEAP. So GDP, our projection of GDP into the future, is not made using the interp function. It is made using another expression called growth. So growth grows a variable at a particular percentage increase per year. And in this case, it is a 10% increase per year. And you can see that this becomes a very large increase over time. So this is perhaps not realistic, but this is just an example. But this growth function can be used to increase over time. And you can see here that this growth function is referring to another variable as well. It is referring to this GDP growth. So that's our key assumptions. Let's get now into our different sectors and look at how we put in our different methodologies for estimating emissions from our different sectors. So we are now underneath demand. You have 7 subsectors: residential, commercial and public services, transport, industry. Let me show you some examples as to how the emissions are estimated. Let's take commercial and public services as our example. So if I go back to current accounts, I'm just looking at what things were like in 2010. So I have an activity level. This is an estimate of how big this sector is. And we can see that the activity level is the GDP times by the value added by services. So we are assuming that the commercial and public services sector is represented by its economic contribution to our country or to our city. We then have a final energy intensity, which is saying per US dollar, per unit of GDP from the services sector, how much energy is required. And you can see that this is not directly input into LEAP. It's calculated with an equation. It's calculated by taking the total energy consumption in units of ton of oil equivalent divided by the total activity. So we have the total activity here from our GDP. The total consumption is entered directly. So this can be obtained from a national or a city energy balance if you have such a thing. This data is something that is generally quite commonly available. And we can enter this directly to calculate our energy intensity. And then that is split by fuel share. So this is the percentage of that energy that is consumed as different types of fuel in this sector. So we can see in this sector the majority of the energy consumed is consumed as electricity. Then 27% is consumed as natural gas. Then if we look down here at our different fuels, for electricity we don't have anything underneath it because there are no direct emissions associated with using electricity. But for natural gas, there are. We've got our 11 different pollutants, and then we have our emission factors stored under this tab, average environmental loading. And this then tells us what the emission factors are for these different pollutants. And the question that people always ask me after I present this is, what does these letters mean at the end? Well, the question mark tells LEAP to ignore what comes after it. So ignore the letters here. They are for us, and they reference these notes. So they provide a reference to tell us what the source of those emission factors are. So if I look at carbon dioxide, 56.1 metric tons per terajoule, and the reference is A. So I know it comes from the IPCC Tier 1 default emission factors. For NOx, the reference is B. It comes from the EMEP EEA Tier 1 emission factor. All of these can be very easily changed. If you have better emission factors available, we can simply delete it and type in something else. And this provides a good way of documenting your data set. The notes here can be updated and added to document your analysis and your data set. So I want to provide just another example of how, so that's a very top-down methodology. In the road transport sector, we've included 2 methods. The same top-down method, which is called simple, where we have an activity level based on GDP, final energy intensity, total consumption divided by total activity, with the total energy consumption in the transport sector here. And then the fuel share split by different types of fuels: gasoline, diesel, natural gas, and biofuels. And then we have emission factors underneath. But this is where it becomes very important to think about what you want to do this analysis for, what policies and measures you might want to evaluate using this analysis. Because if we think about what policies and measures we might want to look in the transport sector, we might want to increase vehicle emission standards. So we might want to go from Euro 4 to Euro 6 vehicle emission standards, for example. I don't know what the regulations are like in South Africa. We might want to have policies where we have modal shift, where we increase the number of journeys that are taken using public transport. Using this simple methodology, it becomes really difficult to represent those types of policies and measures. There's no place here for buses, where we increase the number of buses to increase public transport. There's no place here where we say how many of our vehicles meet Euro 6 standards to look at vehicle emission standards. So it's really difficult to represent those type of policies using this method. That's why we've included this detailed methodology here. So in this detailed methodology, it's more bottom up. The activity level starts with the number of vehicles, so the total number of passenger cars, light commercial vehicles, heavy duty vehicles, buses, etc. And then it breaks it down. What percentage of those passenger cars are gasoline, diesel, natural gas, electric? And then what percentage of those cars meet different types of vehicle emission standards? And then finally, what is the average distance travelled, the number of kilometers travelled by one of those vehicles in a year? And then we combine that with information. Our energy intensity is our fuel economy. How many litres of fuel does it take to travel 1 kilometre? We combine all of that together with our emission factors for different pollutants to then estimate the emissions from the road transport sector. And I hope it's clear that now, at this level, we could increase the percentage of vehicles that are Euro 6 in our scenario to be able to represent those. Or we could increase the number of buses we have and decrease the number of passenger cars to look at shifting to different types of vehicles. So we have more options for looking at different policies if the data is available to do this more detailed method. If we then move on to our transformation sector, we have electricity generation. The way in which electricity generation is represented here is very simple. We can look at LEAP in more detail. There are more complicated methodologies that we could use here if it's a key sector to look at. But the key thing that I want to say is that we do not enter into LEAP the amount of electricity that is produced. That is calculated by LEAP under demand. So we told LEAP how much electricity was generated or how much electricity was consumed in commercial and public services. That then comes through here to electricity generation. So we don't tell LEAP how much electricity is generated. We just tell LEAP how it is generated. So how much electricity is generated using different types of fuels and technologies. In this country, the major source is natural gas. And we say how efficient is that process, which determines how much fuel is then consumed and what our emissions are from those different processes. So we also have our oil and gas, our charcoal making, coal mining represented under transformation as well. And then finally, In our non-energy sector, we have a variety of different methodologies that have been entered to estimate emissions from our different non-energy sources. So we have industrial process emissions, minerals, chemicals, metals, food and drink. And if we work our way down the branches, we can then get to our individual sources. So we have cement production here, and the emissions are calculated under this branch called non-energy effects loaded. This is a useful branch to start at because it tells us the equation that is used to calculate the emissions. So we have the production of mineral, the production of cement, times by an emission factor. So we can enter here how much cement is produced, and we have default emission factors for particulates coming from cement. We have the same for the production of different chemicals. We can put in how much fertilizer and other types of chemicals are produced. Then we have an emission factor to calculate the emissions of different pollutants from that production. Under agriculture, we can have some more complicated methodologies with more variables. So if I choose as an example agricultural residue burning, which can be a large source of air pollutant emissions. If I click here, I have 6 or 7 or 8 individual tabs here. But if I go to the non-energy effect loading, I can get an understanding of what is going on. So the emissions from burning the residue from rice is calculated as the total residue burned times by an emission factor. So I've got my emission factor here. I then have the total residue burned here. So we have annual crop production times residue to crop ratio times dry matter fraction times by fraction burned in fields times by fraction oxidized. So you might be thinking, oh, how much data do I need to be able to estimate these emissions? Well, we have default values for most of these sources. So annual crop production, that's specific to a country or to a city if you have some agricultural areas within Chwane. But for our residue to crop ratio, the amount of residue per ton of crop produced, we have defaults. Dry matter fraction, defaults, with the source of these defaults included here. The fraction burned in fields also have the defaults. So while some of these methods include a lot of data, the actual include a lot of variables. The actual data that you need to find and enter is usually just 1 or 2 variables. So the final thing I want to show you is how we can create scenarios and how we then view results in LEAP. So I want to quickly create a couple of scenarios. Let's say we want to have clean vehicles. So I've gone into scenarios here, and I am just adding some scenarios. Let's create 2. Clean cooking. So I've got clean cooking and clean vehicles, and I've entered them under my baseline. The reason that I've done that is because before I make any changes in these scenarios, all of the variables, all of the expressions, all of the equations in clean vehicles and clean cook stoves will be exactly the same as the baseline. They inherit those expressions from the baseline. And that is really good because it means that we only need to make changes in those key sectors that we are interested in to be able to represent the implementation of different policies and measures. Everything else stays the same. So I've created my 2 new scenarios, and when LEAP refreshes, I'm going to click on my baseline first, and let me go to my transport sector. Now I have to use simple transport because I don't have the data entered for detailed transport for Asiana. So this is my baseline. The amount of vehicles using diesel, using gasoline, using natural gas is projected to stay the same. If I click on clean vehicles, it's the same as my baseline. But I want to make changes. I want to get rid of diesel because it's the most polluting of these fuels. I'm going to represent a policy. It's going to start in 2019. By 2030, I'm going to have phased out diesel and replaced it with gasoline. So interp 2019 baseline value. Now this baseline value just means I want it to be the same as in the baseline. Then in 2030, 0. So now you can see the graph has changed. I've now represented my policy. Get rid of diesel vehicles by 2030. And we can see that they are then replaced with gasoline. I could replace them with electric vehicles, with something else if I wanted to. But that's all I need to do to represent that policy. Let's then look at clean cooking. So we go to residential cooking. I can see that there are people here cooking using traditional wood stoves, traditional charcoal stoves. There are quite few. People also cooking using kerosene. So I'm going to then put in an expression that says interp again 2019 baseline value 2030 0, and I can just copy. I'm going to paste that expression for under charcoal stoves as well, and under kerosene. But what I need to do now is say, well, what is the alternative? What are people going to cook with instead? And it's going to be natural gas. But I don't need to calculate the percent share. I don't need to subtract all of these and work out what number needs to put into natural gas. I can enter this expression here that says remainder 100. That just means LEAP does the work. Add up everything and put the remainder under natural gas. So it ensures that everything adds up to remainder 100. Okay, so now I've created my two scenarios. Let's finish by looking at the results. So, while LEAP is calculating, I'll explain what it is doing. LEAP is taking all of the data that we've entered, all of the variables, all of the information on population, on GDP, on energy consumption, multiplying those together to calculate the total energy consumed, multiplying that by the emission factors to calculate the emissions. It then goes to the IBC, outputs the emissions. IBC models atmospheric transport, atmospheric dispersion, chemical reactions to calculate the impact of that those emissions are having on PM2.5 concentrations, and then calculates the impacts that those have on human health in terms of premature mortality. So while LEAP is calculating, I also want to show you how you can sign up for LEAP and how you can download LEAP. So if you go to the LEAP website, which is energycommunity.org, you will see a screen that looks a bit like this. It should have some news here. I'm not quite sure why that didn't load. But I'm now signed in as me. If I log out, when you get to the LEAP website, you should see this button here called Sign Up. If you click on that button and enter the information here, you can then register as a member of the LEAP website. LEAP operates on a license system, so you should apply for a license. Now, in general, in South Africa, the license, there is a cost to the license, but that has been waived for this project. So once you've signed up, please send me an email and we will then issue you with a LEAP license. And then you can go to this download button. Once you are logged in, you can go to the download button and download LEAP. And I would recommend downloading the 32-bit version of LEAP. You can click download now. You can also access training materials and a user guide for LEAP. And there is a discussion forum here. So you can discuss LEAP. You can ask questions on this discussion forum. You can also search to see if a question you have has already been answered. And you can also see people in your community who are using LEAP. So mine defaults to the UK, but we can look at South Africa and see who within South Africa is using using LEAP. You can see that the person who has there are people in the Department of Energy, City of Cape Town, University of Johannesburg, quite a lot of people who are using LEAP, and you can look at who is the person who has visited the LEAP website the most. So you can see other people who are using LEAP that may have data or may have guidance that could be useful. So that's how you can sign up, how you can download LEAP. So now it looks like it's calculated. So let's have a look and see what results we can look at. So I'm going to show you two types of results. The first are emissions. So let's look at our emissions of a pollutant. I don't know which pollutant you would most be interested in. Let's pick PM 2.5. And you can see that it's projected to increase a lot, which seems completely unrealistic and is due to that increase in GDP that we had. But this is just an example, so I think it's okay. So we've selected the top branch here, which means we see emissions from all of the sub-branches. And they are split. The bar here is split down one level. So we see transformation, demand, and non-energy split. But that doesn't tell me very much. It doesn't tell me the specific sources that are contributing. So if I increase the levels to 2, I can then see something that's much clearer. So I can see the main source here is transport. Then we have industry, and then we have agricultural energy use. That looks like my major sources in 2050. Then I can click group small to make it even clearer. Transport, industry, electricity generation, agriculture are our major sources. And this is our baseline scenario. We can change that to be our clean vehicle scenario, for example. And the graph will update and looks a bit different. So if I click avoided versus baseline scenario, and I pick a different pollutant like black carbon, I see here that I have substantial reductions in black carbon emissions by switching from diesel to gasoline vehicles. So I can reduce my black carbon emissions a lot by switching from diesel to gasoline vehicles, and I can look for other pollutants as well about what effect these scenarios can have. So I'm able to compare different scenarios. I'm able to look at avoided versus baseline scenarios to see what the effect of implementing these policies are. The impacts from the benefits calculator, the IBC results are stored under indicators. And I can first look at PM2.5 concentrations. So let me go back to my baseline scenario. So if I look at my PM2.5 concentrations, I'm just going to select 2010 because I think the results for other years are unrealistic. If I select 2010, I'll just show you how what it looks like. So we have a contribution from natural background to our PM10 concentration, PM2.5 concentration, which is about 50 micrograms per meter cubed. We then have a contribution from NOx, from SO2, from ammonia emissions, and from organic carbon and black carbon. So I can't just consider PM2.5 emissions, I need to consider all of these precursors as well. If I increase my levels to 2, I then get a different split. I get the contribution to PM2.5 concentrations from natural background and from national emissions and the rest of the world emissions. So this tells me how much of the PM2.5 concentration in my country or in my city I am in control of and that I can reduce by taking action, and how much my neighbours need to control and how much is from natural sources. I can then look at what that means, what impact that has on human health. So if I click on premature deaths and then PM2.5, I can see first the age categories that are affected. So how much of this is elderly people, 50 to 70 years, 30 to 50 years. If I increase further, I can see what diseases people are being affected by. So heart disease and stroke are the main diseases that are associated with premature death from exposure to PM2.5. And then I get the contribution from different pollutants, the same as for my PM2.5 concentrations, and the contribution from national and rest of the world emissions. That is a very quick overview of LEAP-IBC. I hope it has been useful. I think the next step is to answer any questions that you have. In terms of how we would move forward with developing a data set for Chwane, I think there are some things that we need to consider and that we should have a call to discuss. The first things that we could put into the development of a work plan would be training to use the software, and we can provide you with written training exercises. We can then discuss them online, as well as having a workshop in South Africa to work on those exercises together to make sure you feel comfortable using the software and how it works. Then we would develop a plan for developing a data set for Chwane, and that would include data collection efforts, so trying to identify what data is needed and what data is available. We would discuss what modelling methodologies we'd use for different sectors in LEAP, and then we would discuss the scenario analysis, how we would create a projection for the baseline scenario, how we would what mitigation measures we would want to represent within LEAP, and how we would represent them, how we would model them. So please let me know if you have any questions, and send me an email, and we can set up a time to talk and to discuss how we move forward once you've looked at this presentation. Thank you very much.